So, hello everyone. Welcome to this presentation on design and optimization of butterfly valve disc using numerical simulation. We are having to move to an online format due to the unforeseen circumstances. Our thoughts and prayers go out to everyone who's battling with COVID-19. All right, let us begin. So, this is the general outline of the presentation. You could take a quick look. Okay, so let us move on to the introduction. So what is a hydroelectric power plant? Well, it is basically a kind of a transducer, an organized transducer in which energy is converted from hydromechanical energy into electrical energy. And since a high velocity flow of water is getting in and out of the power plant, we use various control devices which are known as valves. We use them for a number of reasons: in order to regulate the flow of the water and to stop the water into the turbine in case of certain emergencies, and also in order to assist the inspection of various parts such as the penstock. There are two classifications of valves. The first is the spherical valve and the butterfly valve. The spherical valve is employed for hydroelectric power plants running on head above 200 meters, and the butterfly valve runs for heads that are below 200 meters. In this slide, we are concerned with heads below the 2 meters, so we are using the butterfly valve. We are using the reference butterfly valve from the Foucault Cornali hydroelectric project, the gross head of which is 169 meters. The design flow rate is 63.5 meter cubes per second. The nominal diameter is about 2800 meters, and the disc is made up of cast steel. Below you can see the various properties of cast steel. Now, the objective of our research was to optimize the butterfly valve design using numerical simulation. And in order to do that, we needed to find the stress distribution and the deformation for different models, and we used ANSYS structural to do that. We needed to find the flow distribution for different models, for which we also used ANSYS Fluent. And finally, we calculated head losses in order to compare between the different models. So, methodology. We first collected the literature and reviewed the content. Then we we made educated guesses, I guess, in order to assume different values for different parameters. Then we selected the specific optimization parameters, and then we reduced the models according to the Taguchi orthogonal array. And then we performed numerical simulations as stated above, and then we went into the project. So, valve parameters. We selected three major valve parameters, which are the valve disc thickness, the valve rib thickness, and the rib height, as you can see in the picture depicted. In order to design the butterfly valve, we used three values for the three parameters, giving us a total of 3 times 3 times 3, that is 27 different combinations. And in order to reduce this model to only 9 combinations, we used the Taguchi orthogonal array. And this is the structural simulation. In order to simulate, first we made the CAD model in the ANSYS Space Claim R2, and the CAD model was based on the parameters of the rib height, rib thickness, disc thickness. The shaft diameter and the fillet were additional, and the shaft diameter and the fillet were constant for all models. And after designing, the meshing was performed. Unstructured tetrahedral meshing was used for the discs, and then structural mesh was used in the shaft. The body sizing was 40 millimeters, and mesh independence parameter was of the total deformation, and the convergence was 1%, which is a good value. So we used the structural simulation ANSYS and settings. The hydrostatic pressure was set to 1.5 times that of gross head. The shaft diametrical, the cylindrical surface, the surfaces were assumed to be frictionless support. The displacement X and Y as in the displacement of the shaft about x and y direction were set to be 0, and about the z direction were set to be free. And after simulation, we obtained the data as follows. We obtained the stress distribution to be maximum of 262.9 megapascals in the transition, and it was lower than the maximum stress. And since the yield stress is 415 megapascals, it was a good value. The total deformation was maximum in the upper middle rib, and the maximum deformation was about 1.552 millimeters, which is less than the compression deformation, which is 3 millimeters of pre-compression. This is the result of the maximum stress and the total deformation for different combinations, the 9 combinations that we talked about before. And after that, we also did the CFD simulation. The fluid domain was created from structural domain, and the pipe was extended 2 times the diameter in the upstream, and then the pipe was extended 8 times in the downstream. The mesh independence was done, as in it was tested. The model used was SST-K omega model. The Y plus value was found to be 350 meters, which is well within the range. The first layer thickness was about 1.84 times 10 to the power minus 3 meters. And the inflation growth rate in the direction of Y was 1.2. The mesh convergence parameter was set to be the head loss, and the convergence criteria was 1%. And the unstructured tetrahedral mesh was done in the valve domain. Structural mesh in the upstream and the downstreams. The number of elements that were created was around 1,073,673. The maximum skewness found was to be about 89.94%. Of the other models, the facing size was 40 millimeters and the body sizing was 200 millimeters. These are the boundary conditions and the simulation setups, as you can see, as we already stated above. You can take a brief look at it. And after that, in order to compare between the different models, we also calculated the head loss. The maximum effect was found in the rib thickness, and the minimum effect was found due to the disc thickness. So the rib thickness had the maximum impact on head loss, and disc thickness did not impact the head loss a lot. In conclusion, all the models were structurally sound, both from yield and total deformation point of view. The first model was selected as the final design based on the head loss, since it had a lower head loss in comparison to every other model. The maximum stress of the model was found to be 262.91 megapascal. The maximum total deformation was found to be 1.552 millimeters, and the head loss was found to be 1.062 meters. In this way, we optimized the design of the butterfly valve. Thank you very much for your time. These are the references that we used. Thank you.